What if I told you that you, the screen you're looking at, and even the air between you and the screen are all made of the exact same stuff? Seriously, not similar stuff, but the very same fundamental building blocks, just arranged in different ways. Today, we are digging into the story of the atom, an idea that started as just a philosophical guess and ended up becoming the bedrock of all modern science. So let's dive in.
Okay, so let's start with a little thought experiment. Imagine you've got an apple. You cut it in half. You take one of those halves and you cut that in half again. Then you do it again, and you just keep going. So the question is, could you do that forever? Or would you eventually get to a final, fundamental piece of apple that you just can't cut any smaller?
You know, this question, it's not some new high-tech problem. It's ancient. For thousands of years, this was a huge philosophical mystery. Thinkers all across the ancient world were grappling with this exact same concept, long before we had any of the tools to even begin to test it.
And what's really wild is how this same idea popped up in different places totally independently. Around 500 BC in India, a philosopher named Maharishi Kanad came up with this idea of Parmanu, the ultimate indivisible particle. Then, just about a century later in Greece, Democritus proposed a nearly identical concept, and he's the one who coined the word atomos, which literally means uncuttable. For over 2,000 years, that's all it was. Just a hunch, an interesting idea with absolutely zero proof.
And then, the 18th century rolled around, and everything started to change. This whole question about matter moved out of the philosophy department and straight into the laboratory. Scientists began doing these really careful experiments, and they started finding some very strange, very specific rules about how stuff combines.
The first huge clue came from a French chemist, Antoine Lavoisier. He established what we now call the law of conservation of mass. And put simply, it just means you can't create matter out of thin air and you can't make it just vanish. The total amount of stuff you start with in a chemical reaction is the exact same amount of stuff you end up with.
And Lavoisier proved this with a brilliant and actually pretty simple experiment. He'd take two chemical solutions, put them in a flask but keep them separate, and then seal it up so nothing could get in or out. Then he'd weigh it. After that, he'd tip the flask, mix the two solutions, and let them react. Fizzing, changing color, the whole thing. And when it was all over, he weighed it again. And guess what? The mass was identical, down to the last gram. This was a huge revelation. Matter wasn't being lost. It was just being rearranged.
So that was clue number one. Then, another scientist, Joseph Proust, found the second major clue. He came up with the law of constant proportions. Basically, what this says is that a pure compound, no matter where you find it, is always made of the same elements combined in the exact same proportions by mass.
Water is the perfect example here. It doesn't matter if you get your water from an iceberg, from a river in the jungle, or if you make it in a lab. It is always made of hydrogen and oxygen in a mass ratio of 1:8. Always. This wasn't just some weird coincidence. It was a fundamental rule of nature. So now you've got these two big puzzle pieces just sitting there, waiting for a detective to come along and put them together.
And that detective was an English school teacher named John Dalton. He looked at the law of conservation of mass, and he looked at the law of constant proportions, and he had this huge eureka moment. He realized that both of these laws were pointing to a single, powerful conclusion, that those ancient Greek and Indian philosophers, they were right all along.
And Dalton's own story is pretty remarkable. He was born to a poor weaver's family, and he started his career as a teacher when he was just 12 years old. He was this brilliant, self-taught researcher who in 1808 took all the evidence that was floating around and pieced it together into the very first scientific atomic theory.
Dalton's theory was a total masterstroke because it explained everything scientists were seeing in their labs. He proposed that, all matter is made of these tiny particles called atoms. Then he said these atoms are indivisible and can't be created or destroyed. Boom! That perfectly explains Lavoisier's law of conservation of mass. A chemical reaction is just atoms rearranging themselves. And he also said that atoms combine in simple whole number ratios, and that's exactly why water always has that 1:8 mass ratio. It wasn't magic, it was math. Dalton had cracked the code.
All right, so Dalton's theory was a huge home run. But, it opened up a whole new can of worms. If these atoms really do exist, then just how small are they? And maybe even tougher, how on earth do you weigh something that's impossibly small?
The scale here is just, it's really hard to wrap your head around. A single grain of sand, which is already pretty tiny to us, is 100,000 times bigger than one water molecule, and that water molecule is 10 times bigger than a single hydrogen atom. You could stack millions and millions of atoms on top of each other just to match the thickness of a single sheet of paper. They are unbelievably, fantastically small.
Which brings us to that second massive problem, right? If you can't even see an atom, let alone pick one up and put it on a scale, how in the world could you ever figure out its mass? Well, the solution scientists came up with was truly ingenious.
They decided if we can't weigh them directly, let's just weigh them relative to each other. Think of it like this fruit seller. He doesn't have any standard weights, so he improvises. He grabs a big watermelon and just declares, this watermelon has a mass of 12 units. Then he cuts it into 12 equal slices. Now, one of those slices is his new standard, 1 fruit mass unit. He can weigh an apple and find out, oh, it's about the same as 1 slice. A bunch of grapes might be half a slice. He's not finding the actual absolute mass, but he can compare everything in his shop to that one standard. Scientists did the exact same thing, choosing a carbon-12 atom as their watermelon and defining its mass as exactly 12 atomic mass units.
Okay, so now we've got these tiny fundamental building blocks, and we even have a way to measure their relative weights. But how do they go from being these individual little particles to forming, well, everything? The answer is that they team up, and when they do, they form molecules.
So what's the difference between an atom and a molecule? Think of it like this. An atom is the smallest possible unit of an element, like a single Lego brick of a specific color, say a red one. A molecule is what you build with those bricks. Sometimes you stick 2 of the same color together, like the O2 oxygen that we all breathe. And other times you combine different colors, like building a water molecule, H2O, out of hydrogen and oxygen bricks.
But how do atoms know how to combine? Well, they have this property called valency, which is basically their combining power. I love this analogy. Think of valency as the number of arms an atom has. An octopus has 8 arms, right? A human has 2. So if an octopus wants to link all of its arms with human arms, how many people does it need to grab? 4 people. 2 arms each for 8 total. Atoms do the same kind of thing, linking up based on how many arms they have available to connect with.
And using this idea of arms, or valency, chemists have this fantastically simple trick for figuring out chemical formulas. It's called the crisscross method. You just write down the symbols for the elements and their valency numbers. So for example, magnesium has a valency of 2, and chlorine has a valency of 1. Now you just crisscross those numbers. The 2 for magnesium goes down to become the subscript for chlorine, and the 1 from chlorine goes down to become the subscript for magnesium. You get Mg1Cl2, which we just simplified to MgCl2. It's this incredibly handy shortcut for predicting how the building blocks of the universe are going to snap together.
So there you have it, the atom, an ancient idea, proven by chemical laws, and finally defined by Dalton's theory as the final, indivisible building block of all matter. But that leaves us with one last tantalizing question. Dalton called the atom indivisible. What if he was wrong? What if the story of what's inside the atom was really just getting started?